Hi guys, thanks for tuning in on a short lecture about chemical sedimentary rocks and the earth materials or minerals that are contained within them. Let me shrink this down. Okay, so as we discussed in class, chemical sedimentary rocks differ from clastic or detrital sedimentary rocks in that they are formed by the precipitation of minerals from water or by alteration of already precipitated material. Examples of these types of rocks include limestone, dolostone, evaporites, and cherts. We're going to talk about all of those. Typically speaking, chemical sedimentary rocks have names based on their chemical compositions. They tend to contain only one or very few types of mineral. So, for example, limestone tends to be made primarily of calcite, dolostone of dolomite, etc. The most common precipitated minerals have elements with high solubility or are of great abundance. So this is just a photo that I like to include because it's of a region of southern China where you can see there's a river that's flowing through this landscape and it is chemically eroding the limestone bedrock of the region. And so all of these tooth-like mountains that you see in this view are all made of limestone, and they are being chemically eroded by the water or chemically weathered, such that you get these little, like, almost look like thumbs that stick up out of the ground. And so this is kind of an unusual type of erosional pattern that is completely due to the fact that the limestone is being actively dissolved by all of the water, both rain and rivers, that's moving across this landscape. Pretty cool. Chemical sedimentary minerals, like I've said, are formed by the precipitation of ions from solutions or by the chemical alteration of already precipitated minerals. They typically belong to one of three classes: either carbonates, which contain the carbonate radical, we diagrammed that in class on Tuesday; sulfates, not to be confused with sulfides. Sulfates have been oxidized and have a net -2 charge; or halides. So halides are minerals that contain an element from the halogen group, usually chlorine or fluorine minus. And so this is just to give you some perspective on all of the mineral classes. So we spent the vast majority of the semester talking, of course, about silicates. They are far and away the most abundant mineral class on planet Earth. When we talked about ore materials or ore minerals, we talked mostly about oxides, sulfides, and natives. And then today, because we're talking about chemical sedimentary minerals, we're going to discuss halides, carbonates, and sulfates. If I've circled it, it's because it's the most commonly found type of mineral in the Earth's crust. The only other one that I might circle that we're not really going to talk about much are phosphates, and only because phosphates contain the mineral apatite, which is a fairly common accessory minerals in a lot of different rocks. So, in order to make a chemical sedimentary mineral, you first have to have a fluid that contains a lot of dissolved ions, and of course that can happen easily just through the passage of water across rocks and chemical weathering. So you've got water that has a bunch of dissolved ions in it, but what's going to cause those dissolved ions to reprecipitate out of the water and form a solid mineral? Typically that occurs because of one of three factors. Either one, the temperature of the solution changes. So if the temperature decreases, that might prevent dissolved ions from remaining in solution and might encourage them to otherwise precipitate out. So think about how you're able to, throw salt into a boiling pot of water. It instantly dissolves. But if you were to turn the heat off of that pot of water and give it enough time, the salt would probably reprecipitate back out of that pot of water. If the pH of the solution changes, that could also cause minerals to precipitate. And lastly, biological activity can also lead to the precipitation of chemical sedimentary minerals. So in this case, you're looking at two different types of calcium carbonate. On the left, something that we call marl, and on the right, something that we call travertine. Both of these are examples of chemical sedimentary minerals that have formed through one of these three processes. Carbonates very commonly form these ways. We looked at carbonates in lab this week, and you'll recall that they all contain the CO32- radical. Some may contain additional ions or anions or anionic complexes. Far and away the most abundant of all the carbonate minerals is calcite, CaCO3, and right behind it dolomite. Dolomite is simply calcite that also contains magnesium. So because you're adding another ion with a 2+ charge, you've got to bump up the number of carbonate radicals necessary to balance the charge. So you got to have 2 CO3s in the formula of dolomite. Calcite also contains what we call isostructural minerals, and I'm going to get to that in the next slide. Those include siderite, magnesite, and rhodochrosite. Rhodochrosite you saw in the lab on Tuesday. We call these minerals isostructural because iso stands for same and structural obviously means structural. So what it means is that these minerals, while they have different formulas, so magnesite contains magnesium, siderite iron, rhodochrosite manganese, they all have the same structural or same structure. So the cations, manganese, magnesium, iron, calcium in the case of calcite, are all organized the same way relative to the CO32- radicals in the mineral structures. Pictures of these three minerals are shown here. On the left, magnesite, forming these nice kind of blades or tabs. Rhodochrosite on the bottom left. Rhodochrosite almost always has this really characteristic kind of hot pink color. It's really beautiful. And then in the bottom right is siderite. You saw some, I can't remember now if we had siderite in our lab or not. Usually you can distinguish siderite from some of these other species because it will actually, the density or the specific gravity of siderite will be noticeably higher. You'll feel it, it'll have like a greater heft in your hand when you hold it. Okay, aragonite. This is something that we did not look at in lab. Isn't this a cool picture of aragonite? It always makes me think of bananas every time I see it. Aragonite is a polymorph of calcite. So I'll remind you for the millionth time that polymorph is something that has the same chemistry but a different structure. So it's actually kind of the opposite of the isostructural minerals we were looking at, which had the same structure but different chemistry. So aragonite is also CaCO3, but if we look at the phase diagram over here on the right, which has temperature going up to the right and pressure going down toward the bottom, you can see that the stability field for calcite is in the kind of lower temperature, lower pressure zone, whereas aragonite is stable at higher pressures. Aragonite doesn't form commonly or as commonly in the earth today as calcite does. Dolomite, like I've explained, is similar to calcite and calcite's isostructural friends, only it also contains magnesium. Okay, so again, if you want to squeeze in a magnesium, you've also got to add in another calcite. It's in solid solution with anchorite, which instead of magnesium contains iron. And I had you look at that in your lab and talk about why, whether or not that solid solution series was complete and what that might mean. At the bottom of this ternary diagram, we have magnesite and siderite, and those two are in complete solid solution. Carbonate sediment, whether it be calcite, aragonite, dolomite, any of those carbonates that we just discussed, can be classified as either chemical or biogenic. If it's chemical, that means it precipitates directly from a solution. So you've got, water in an ocean of some kind, and it's got a whole bunch of dissolved ions in it. Eventually that water reaches what we call supersaturation, meaning that it is completely saturated with those dissolved ions and can no longer support that level of saturation such that the ions are going to start to come together and form bonds and precipitate solid, naturally occurring crystalline materials, aka minerals, in this case, chemical sedimentary minerals. And as we've discussed, that could happen because of a change in temperature, a change in pH, or maybe you get a, the interference of an organism. In that case, we're creating a biogenic carbonate mineral. So biogenic creation of carbonates refers to the secretion of shells or skeletons by living organisms of carbonate mineral. So they are actually taking the dissolved ions out of the water and using them to precipitate their shells. When those organisms die, their shells essentially rain down onto the seafloor where they can be broken up and turned into clasts of material that later get cemented to form sedimentary rocks. And so that's kind of an in-between area between clastic and chemical sedimentary rocks, because the materials are detrital in nature, but they are made of chemical minerals that are precipitated with the aid of these organisms. And so there's some really cool photos here of some of these, many of them microorganisms that live in the oceans and secrete carbonate shells, which they draw from the seawater. Incidentally, there are also other organisms that secrete silicate shells. So they take, instead of drawing CaCO from the oceans, they draw Si and O from the oceans, which are also dissolved in seawater. It's possible to have what look like organic materials that are chemically precipitated. So in this case, what we're looking at are something called ooids. Ooids are super cool. They are carbonate grains that are developed around kind of a little seed or a nugget of carbonate that then gets rolled back and forth, usually at the bottom of the ocean in a wave zone. And new carbonate material chemically precipitates around that little seedling in concentric layers. These are inorganic, so they form completely chemically through direct precipitation from seawater. And if you were to take one of these kind of round spheres and cut through it, you'd see what is shown on the right, which is a photomicrograph. So this was taken with a petrographic microscope. You can see that unlike the photo I showed you guys in lecture today, this one actually does have a scale bar. And if you look closely, you can see it's got this central kind of seedling, and then it's got some concentric layers that are developed around it. And those form as this little sphere is rolled back and forth in the wave zone. Carbonate sedimentation can occur in a lot of different settings, most of which are associated with the shallow oceans. So in this picture, this is kind of a cartoon picture that's meant to represent all of these different places and ways in which you can get carbonate sedimentation occurring. So it can happen at or near the interface of the ocean with the land, so around beaches. Here we've got ooids, for example, that are forming in a shallow channel that's developed into the ocean, where you might get, the rolling action of these little seedlings around. You can get calcareous mud forming in really still waters like lagoons. You can get, of course, a lot of carbonate developing where you have a lot of like teeming sea life. So in places like coral reefs and things like that, you have a lot of organic material that's going to be drawing calcium and carbon from the seawater and creating lots of carbonate sedimentation. This picture also shows how evaporites, which we're going to talk about next, might develop in these kinds of settings. And I'll just point out that in order to make evaporites, you're going to need to have some kind of restricted basin. So that's why this little kind of bar is here. That's necessary because if that weren't here, then you'd have access to replenishment of the water, by the ocean in this case. And so you're never going to completely reach supersaturation and cause precipitation of evaporites. And one other thing I want to point out is that there is something called the carbonate compensation depth. So in the oceans, once you get it below a certain depth, you can no longer form carbonate directly from the seawater. And instead, beneath that carbonate compensation depth, you will only have the chemical precipitation of siliceous oozes. So these are things like chert. Okay, chert is microcrystalline quartz essentially. So it's siliceous or silica rich in nature. It's super fine grained, and it's basically like SiO that is coming together and forming like almost like an amorphous ooze at the bottom of the deep oceans beneath the carbonate compensation depth. Okay, evaporites. Evaporites can be carbonates, but more typically they are halides and sulfates. These tend to form in restricted basins where evaporation raises the concentration of soluble ions to supersaturation levels. So in this case, it's temperature that's going to drive water off of your, or drive water out of your basin. And again, one of the things that is required by these systems is restriction. So if you have new water coming in, then it doesn't matter how much water you evaporate away, because you'll always have influx of new water, so you're never going to reach supersaturation levels. But if your pool of water is restricted such that it can't be replenished, and you're evaporating that water away, then the water that's the ever decreasing volume of water that remains is going to have a higher and higher concentration of dissolved ions in it, until eventually it gets to the place where those ions can no longer be sustained in solution and are forced to come together and make bonds and form minerals. Typically, evaporite minerals form kind of in a sequence. So the early evaporite minerals tend to be carbonates, like aragonite, calcite, dolomite. And it's only until you get to kind of more hyper-arid environments where you might start to precipitate gypsum, the sulfates, gypsum and anhydrite, and then last to precipitate under the most supersaturated conditions. Only then will you get halides, such as halite. Okay, in the other direction, the next way of looking at it is that halite, if you were to have, say, a bucket with all of these minerals in it, aragonite, calcite, dolomite, gypsum, halite, and you were to splash a bunch of water into that bucket, halite would be the first to dissolve. So it has really high solubility. So last to precipitate, first to dissolve. So if you see, a crust of halite on, say, a shallow basin somewhere in, say, Death Valley, or in the Mojave Desert, that is a really hyper arid environment where you've really had to drive off all of the water, and then finally in the last gasp you might get the precipitation of halite. It's not going to be early forming. Many times, or a very common evaporite that forms are sulfates, and so the most common of all the sulfate minerals are gypsum. Oops, that should be a Y. Gypsum, which is a calcium sulfate, and anhydrite, which is just its sister without the water. Gypsum and an anhydrite, not surprisingly, are commonly found together, and frequently they form what we call varved deposits. So in this picture, we're looking at varves of gypsum and anhydrite. So every darker light band that you're seeing is gypsum or anhydrite, and basically what they're representing is kind of a continuous record of chemical sedimentation in an arid evaporitic environment. And because we're fluctuating between gypsum and anhydrite, that's telling us something about seasonal changes in the climate, where we're going from wet seasons, or I should say relatively wet seasons, where you might precipitate gypsum, to drier seasons where you might precipitate anhydrite, and then back to gypsum, in the winter months and then anhydrite in the summer months. That would be the case for, say, our climate where we get all of our all of our precipitation in the winter. If you were in, say, if these were forming in, say, Arizona, where they have a summer monsoonal climate, then you would have the opposite would be the case. And so they tend to form these very finely laminated layered deposits that we call varves or varved deposits. Here's another picture of varved deposits. One thing that's really cool about them is that varved deposits should form nice, planar, horizontal beds because, again, these are sedimentary rocks and the law of original horizontality applies. But instead, what we typically see in these varved deposits, or commonly see anyway, are these really complex structures. Some of these structures are related to soft sediment deformation. So imagine that you have kind of like oozes that are kind of deforming thanks to their own weight in the basin. But then some of it is post-depositional structural change. So you can see some faults. I'll mark a few of them here. These are, very small in scale, of course. Millimeters, probably, maybe up to centimeters, in this case. But they can be kind of interesting structural markers, these varved deposits. So they can tell you a lot about climate or paleoclimate, depending on how old the varved deposits are. And they can tell you something about, structural deformation of the area as well. And then I couldn't resist drawing in one more picture of these varved deposits because I think they're so cool. So we were just looking at gypsum and anhydrite, okay? We could kind of think about dividing all sulfate minerals. All of these guys, by the way, have the sulfate radical. Some contain water, so we'll call those the hydrous ones. Some do not, we'll call those anhydrous. Again, gypsum and anhydrite are the two most common types of hydrous and anhydrous sulfates. But there are some other types. So if you can substitute, say, magnesium for calcium. That'll get you kieserite. Or you can substitute barium for calcium. That will make barite. You guys saw barite in lab. Barium is a very high Z element. So barite tends to be really dense. That's the easiest way to tell it apart. It has a very high G or specific gravity. That's the easiest way to tell it apart from anhydrite or gypsum. Celestite is another type of anhydrous sulfate mineral that contains strontium. Anglesite contains lead. So these are not going to be as common for obvious reasons because, of course, barite or barium, strontium, and lead are not as common as calcium or magnesium. Antlerite is another one that is a copper sulfate. That one is hydrous. So all of these are potential chemical sedimentary minerals that could form in evaporitic environments, but gypsum and anhydrite are the most common of them all. Some more pictures of gypsum. You might recall in lab today seeing some really clear examples of gypsum. When gypsum is very translucent, we call it selenite. So you saw some beautiful selenite. Selenite can form some really gorgeous twins like what you're seeing here. We saw that in lab. Gypsum crystals, these are also selenite crystals, can become incredibly large. So check out this dude for scale. This is from a very famous cave in Mexico. And some of these gypsum crystals are 11 meters long. That's like 33, 35-ish feet long. Oh my gosh, I think this guy is like 6 feet tall for reference. Isn't that cool? Okay, lastly, halide minerals. Halide minerals are those that contain anions from the halogen group. Remember, this is the group that sits right next to the noble gases. So they always develop a charge of -1, and they are highly electronegative. They are the most ionic of all the minerals. So things like NaCl, KCl, fluorite, those are the top three. So halite, sylvite, fluorite, those are the three most common of the halide minerals. And they are the most ionic, which we define as having the greatest difference in electronegativities. So that's what we mean when we say that something is really ionic. So if we were to take the electronegativity of chlorine or fluorine, which is really high, and then subtract the electronegativity of halite, sodium, potassium, or calcium from that, those have very low electronegativities. So the difference is huge. And so therefore, these minerals are very ionic. So they're going to behave according to Pauling's rules perfectly. So halite and sylvite have the same structure that's incredibly simple, where you just have alternating arrangements of negatively and positively charged ions, like is shown here. Because of that, these crystals, halite and sylvite, and fluorite for that matter, tend to be incredibly symmetrical. They tend to be very simple, and they tend to form crystals that are cubic in nature, with like 3 planes of really excellently developed cleavage that all meet at 90 degrees. In fact, you can actually see those cleavage planes here. Like there's one, and there it is repeating. You see that kind of like stair-step pattern in the halite right there. Pretty cool. Okay, another type of chemically produced sediment that we haven't talked about, banded iron formations. I'm going to show you one of these in person when we get back to the classroom next week. These are a really important source of iron ore. They are actually native iron that precipitated kind of like an ooze, if you will, and formed these like banded formations. That's why they're called BIFs, banded iron formations. What's interesting about them from like a broader geologic or tectonic context is that we only find them on planet Earth between about 3.8 and 1.8 billion years ago. So planet Earth has not made banded iron formations for the last 1.8 billion years. And so there's some ideas around this, but probably what happened was that the Earth in general became too oxygenated. And so iron, wherever it was forming, tend to develop into, to become oxidized and to make, hematite, magnetite, other types of iron oxide or iron silicate minerals, instead of precipitating directly to form these really interesting banded iron formations. And the very last thing that I want to tell you guys that's interesting about these salts, so things like halite, sylvite, fluorite, but also some of the other slightly less soluble materials like gypsum, they can actually have really interesting physical properties wherein they can flow over large distances and over long time scales. They're solids, they're crystals, but they are actually capable of flowing kind of like silly putty, and they tend to be more buoyant than the rocks around them. So again, if given lots of time, this is not something that happens rapidly, but over geologic time, it is possible for these salts to rise almost like blebs in a lava lamp and form what we call salt diapirs. So this form that you're seeing here, I'll kind of trace it, that has that kind of lava lamp style pattern. On the right, by the way, this is an image that was made with geophysical recording devices. So what you're looking at are essentially like, you can think of them as being like acoustic reflections. And so if I were to trace that form, you would see it again here. It would look something like this. Okay, so that's a diapir. And people are really interested in these diapirs for a number of reasons, but one of the big reasons that they're of interest is that they tend to make excellent traps for oil production. So you can see here that as this salt dome or diapir on the left rises up, it kind of breaks through these rocks and it can form a really nice kind of cap. So any oil or gas that might have been down here in this black zone is going to kind of migrate over to the salt dome and then get stuck kind of underneath this kind of bulbous top part of the diapir. And so the oil and gas it forms like a natural trap. And then you can go and put an oil well up here and excavate or drill out that, suck out, I guess is really a better way of thinking about it, the gas that might be trapped by one of these salt domes. Incidentally, a lot of the oil and gas reservoirs that are in the Gulf of Mexico form this way because at depth in the geology beneath the Gulf of Mexico, there are evaporite layers. And some of those evaporite layers have developed these big diapiric structures that create these natural traps for oil and gas. And so there are actually a lot of images like the ones you're seeing on the right where oil companies are going out and they are collecting seismic survey data to try to find these diapirs. And then they might go and, look for little plays like where, oil might get trapped right there, for example, if it's a, oil-rich horizon. So that's an interesting feature of these salt domes. Okay, I'm going to end it there. Thank you for following along and watching with me. I'll see you guys back in the classroom.